Right, 9.4, collisions in one dimension. Basically, we have two types of collision. Number one, we call it as elastic. Number two, we call it as inelastic. Elastic and inelastic. Now, what's the difference? In elastic collision, there are two things that are conserved. Number one, momentum. Number two, the amount of total kinetic energy. Amount and total. Okay, total kinetic energy. Now, what's the difference between elastic and inelastic? In elastic collision, the total kinetic energy is not conserved. As simple as that. However, it still conserves the momentum. Now, so what's the similarity? Similarity is that both conserve. Similar, conserve momentum. Differences, inelastic does not conserve kinetic energy. Does not conserve total kinetic energy. Okay, from that version as well, we have what we call as perfectly inelastic. Perfectly inelastic. Perfect here represent that it doesn't conserve the kinetic energy, of course, okay? And definitely it's tangled, melekat with one another. So the moment that it's melekat, definitely it's inelastic. Alright, in the scenario whereby two cars bump into one another but somehow get separated, we call it inelastic if the kinetic energy lost. But if it's not lost, then we consider that as elastic collision. Now, effect of knowing or understand the concept of inelastic that left you with only one expression. Cuma pakai satu rumus sahaja bila dia sebut inelastic, which is conservation of momentum. Conservation of momentum, and that's it. Alright, when you are in the idea of elastic collision, kita kena tambah one more expression. And that expression, number one, is conservation of momentum. However, the number two expression is this one, 9.2, or you can written it as U1 minus U2 equivalent to V final minus V1. The same one. It's just the way of the writing. Now, this expression is actually a combination or a simplifying version when you agree that kinetic energy is supposed to be conserved. When we combine, rearrange these two expressions, we arrive with this one. Therefore, if you have elastic collision, in short, you have this expression to be used and also this expression to be used. Okay, let's now turn to example 9.5. In this example 9.5, you find that the scenario would not be asking for force. However, you find there are interactions between objects, and the object in these scenarios are two cars. So we have 1,800 car that stop at the traffic light. So this is it, 1,800. It's struck from the rear by a 900 kilogram car, a much smaller car. Okay, we find after that they are entangled, maknanya dia melekat, and then moving along the same path. So moving along the same path as that of the original moving car. So we still find that this example object is moving in one dimension, which in this case probably to the x direction. So if the smaller car is initially at 20 meter per second before the collision, so right after they touch one another, they make contact with one another, they collide with one another, what will be their final velocity? Now, this is the case whereby asking final velocity required us to go back to conservation of momentum. And for that, conservation of momentum, the jotting down of the process would be the initial momentum whereby comes from the smaller car. So which is 900 times 20 meter per second. What about the 1800? Null, 0. Okay, and because they are entangled, so you find that they should have the same V together. So we can factorize the mass 1 plus M2. Okay, we factorize V final, and therefore you find that the overall final velocity gets much smaller. Okay, get much smaller. Now, it's also interesting to look at the what if. The what if discuss, what if the scenario is reversed, where now the stationary is the 900, the smaller version, the smaller car, while the 1800, the larger, is moving. Okay, it's moving. So we find that from our calculation, we arrive that our final velocity belonging to the 900 kilogram, the same mathematical version. It's just that the reverse positioning. Alright, and you find that it's actually double, almost double. Why? Because we find almost 2 times. Now, do not memorize. You are supposed to do the calculation. But the whole idea, because of the system, has an initial larger momentum. So, the larger the object, even though it might be moving with a small velocity, it has large momentum. Now, in example 9.6, whereby the title Ballistic Pendulum, we are going to see a scenario whereby a bullet is supposed to hit or make contact with a pendulum. And this pendulum will therefore acquire kinetic energy, menerima kinetic energy, and then swing. Okay, so you will find the scenario involve 2 situations. When the bullet hits or make impact with the block, that is the momentum. And then afterward, that it swing, that is the energy conservation. Alright, this is an example which is very similar to our textbook. However, this one has value, so we are going to use this one. So the scenario is that you have this ballistic pendulum as a device that used to measure the speed of any moving object. So in this case, it's a bullet. So this bullet will be fired, and then it will hit the blocks or woods that is suspended by like wires. Now the bullet is stopped. Stop here represent or hit. Okay, stop because it's purely embedded. So term stop here to represent that is embed together. And as they embed, and now the blocks has acquired ataupun menerima kinetic energy, it swing to a height of h. Now, so looking at the concept, where does momentum occur? Momentum occur because of there is contact. There is collision. Okay, there is a collision between the bullet and the block. So writing in a form of conservation of momentum, mass of the bullet times the initial speed, its initial speed, is equivalent to the product of they embed together. So M1 together. And as they swing or start acquired V, so this V is V after impact. Okay, after the V after impact. Now, with that after impact V, where we call it as V system, okay, V system, then go to the conservation of energy, or perhaps this ideal energy final minus energy is equivalent to 0, because we're not supposed to see there is friction. So this is a case where there's no friction, there's no energy loss. Right. So the energy at this location, provided that M1 plus M2 is M, so mgh, okay, I am writing it in a large M, capital M, so that it's much easier for you to observe and cancel out, right? So mgh, so this is the h that we are talking about, minus the energy at this location. So if we can say final here would be here, and initial is after the impact. After the impact. And you find that from your calculation, you can actually simplify the version later on. Okay, now let's look at what's given. It says here that the bullet is 5 gram. So here we have 5 gram. Remember that it should be SI unit. So you have to convert into kilogram. That's number one. The blocks itself is 1 kilogram. So this one is 5 to the power of negative 3 plus 1 kilogram. Alright. And the H is 5 centimeter. The H is 5 centimeter. So this is 0, 0, 5 centimeter. Alright. Of these two expressions, what to do next is by looking at the question. They want velocity of the system. Velocity of the system. They want this. They want this. They want this. However, if we look at our equation, first equation from conservation of momentum, kita tak ada apa? Kita tak ada ni. Kita tak ada this value. We do not have this value. So, rest for a while. Don't look at this equation. Look at the second equation. Conservation of momentum. Okay, now. So, from conservation of momentum, you can see straight away that you have H. You have 9.8 here. And you can now solve what is the V of the system. Okay, let's look at the answers. So, notice that this is the capital M that I have mentioned earlier so that I can cancel out much easier. So you should arrive with 0.99 from conservation of momentum. Now that you have the value after impact, so this is V after impact or V final. Then substitute into conservation of momentum. So you will arrive with 199. So this is the speed belonging to bullet. Okay, give it a try. Now, in example 9.7, you will be given two objects that are supposed to collide with one another, but in between them, there is a spring. So, you will be asked, okay, if the system is elastic collision, the collision is elastic, three things. Number one, what will be V after their collision? And then what will be V during the collision? And finally, the amount of compression at that very specific time. Now, so let's start with number 1A. Now, looking at the figure, we find there are two blocks where the first block has velocity in the x direction, positive x direction as 4. And the second block has negative 2.5. Right? Now, according to the question, whereby it says that it moves on a frictionless horizontal track, collides elastically. Please add this term. So for the exam, they will introduce the version, the keywords, so that you have the idea that the system is elastic. Now, provided that the spring constant is 600 and the same explanation regarding this velocity earlier, you are to find velocity of both when they are separately after the collision. The keywords is this one, the terms after the collision. So after the collision represent that you need to use conservation of momentum, and whatever V final that you are going to calculate after that is considered as V after the collision. Now, so conservation of momentum, that is the first expression that you're going to use. This is how you are going to substitute into the expression. You choose one, so therefore corresponding to the speed. Okay, so what is the speed initially? So accordingly, okay, this is 1.6, so therefore its velocity is 4. Now V 1.6, so velocity as V1, an unknown number, Now, this figure is meant for other question. Untuk soalan B, we are now looking only at A. So, the second block, which move at negative 2.5, has mass 2.1. So, 2.1, after the collision, we are going to jot down as V2. So, after this, if we calculate and get V2, it means that it belongs to the velocity of 2.1 kilogram. Conservation of energy, kinetic energy, allow you to come up with the expression U1 minus U2 equivalent to V2 minus V1. So this is the expression. So U1 is 4, U1 is 4, U1 is 4, minus 2.5 equivalent to V2 minus V1. Now before you proceed, look closely of these two expressions. You do not have two unknowns here, V1 and V2 in both expression. So from here onwards, my suggestion is simplify. V2 is equivalent, for instance, 6.5 plus V1, then sub into conservation of momentum, into the other equation. You will arrive with the answer of 3.12. 3.12. While when you figure out what is V1, okay, substitute 3.12 into equation number 2 or equation number 1. Either way, you will arrive with negative 3.38. So you find that the first block is supposed to move in the backward, rebound, arah bertentangan. So selepas collision, dia patut pergi ke sini V1 dia. It's left. B question, you are to determine velocity of block 2 during the collision if block 1 is moving at velocity positive 3. Now, we agreed earlier from our calculation, right after impact, right after collision, V1 supposed to be rebound with negative 3.38. Here indicated that it has touched the spring, made contact with the spring, but not yet fully compressed. Okay, fully compressed, or else after the fully compressed, it should rebound in negative 3.38 meter per second. So this is a case whereby it occurs during the collision and not after. And because of that, expression that we are going to use is conservation of momentum. It's conservation of momentum because the system has conserved and isolated. Okay, conserve momentum and it's an isolated system throughout the collision. Walaupun tengah-tengah collision tu. So ini case tengah-tengah collision sedang berlaku. So you are left with only conservation of momentum. Substitute the value of 3 just now. Okay, considering the direction as well. So you should arrive with this answer. Give it a try. Now in question C, where it start asking you the amount of compression at that particular instant, okay, referring to question B actually, correlation to B. So we are going to use conservation of energy. Why? Because there is no work non-conservative. There is no friction. System is isolated. How about spring? Spring is conservative force. Okay, including gravity. Alright, write down the expression final energy minus initial energy, or change of K plus change of U equivalent to 0. Substitute accordingly the V that you have calculated earlier, which negative 1.74, okay, and 3. And 3, the value of V that you have calculated, together with the unknown of Kx at that instant, then you will arrive with this answer. Again, give it a try.